The Booster 18 explosion just revealed what SpaceX has been hiding inside Block 3. Engineers spotted a completely redesigned propellant system, no central oxygen tube, reimagined flow paths, a side-mounted header tank never used on any rocket before. Why would SpaceX rebuild everything when the old design already worked? Because Musk discovered one critical flaw that kept threatening those tower catches. And this is exactly how he fixed it. Let's dive right in. When Booster 18's pieces scattered across the Gulf of Mexico on December 17th, most people saw tragedy. SpaceX engineers saw something else entirely, an unexpected gift. For the first time, the internal guts of a Block 3 Super Heavy were laid bare for the world to examine. And what they found wasn't just an upgrade, it was a complete philosophical shift in how rockets should work. Look at the oxygen system first. Every previous Starship had a massive central transfer tube running through the oxygen tank, essentially a pipe within a pipe delivering LOX to the engines. Block 3? That tube is gone, completely eliminated. Instead, the entire outer tank becomes the delivery system. When those valves open, oxygen flows straight down through short, direct feed paths to the engines. No middleman, no complexity. Why does this matter? Because every component you remove is one less thing that can fail during the most critical 8 seconds of flight. Those final moments before tower catch, when even a tiny propellant disruption means the booster slams into the ground at terminal velocity. But here's where it gets interesting. If oxygen gets this simplified treatment, why does methane still need that enormous central tube, the one SpaceX compared to a Falcon 9 rocket? The answer reveals something crucial about the physics at play. Methane sits in the upper tank, separated from the engines by the entire length of the booster. It has no choice but to travel through that reinforced tunnel, and reinforced doesn't begin to describe it. Early in flight, surrounding liquid oxygen crushes inward on this tube with tremendous force. Later, once that oxygen burns away, methane pressure reverses the load, pushing outward instead. The tube experiences forces in both directions during a single flight. Then add the aerodynamic stress of atmospheric re-entry and the structural loads of landing, and you've got one of the most brutally stressed components on the entire vehicle. Most companies would over-engineer this. Add mass, increase safety margins. SpaceX did the opposite. They made it larger, which paradoxically made it lighter. A bigger diameter tube distributes stress more evenly, allowing thinner walls that actually improve reliability while cutting weight. That's the kind of counterintuitive thinking that only emerges when you're building dozens of these vehicles and learning from real flight data instead of simulation. Now for the breakthrough that changes everything. Mounted on the side of Block 3's booster sits something no rocket has ever carried before: a dedicated landing header tank. This isn't a backup system. It's not redundancy for safety. It's the solution to a problem that's been haunting SpaceX since they started catching boosters. Here's what was happening. By the time Super Heavy returns for its tower catch, almost all propellant has been burned. The little bit of liquid oxygen remaining in the main tank becomes unstable. It sloshes. It breaks apart into pockets of gas and liquid. During those critical final seconds when the booster lights its engines for the landing burn, this disrupted propellant flow was creating unpredictable thrust. Exactly what you don't want when you're threading a 20-story rocket between two chopstick arms. The side-mounted header tank solves this elegantly. Throughout the entire flight, ascent, hot staging, boost back burn, this tank stays mostly full and completely isolated. Only after the boost back burn do valves switch over, routing the inner ring of engines to draw from this stable reserve. When Super Heavy fires up for that final landing sequence, it's not gambling with sloshing, disrupted propellant. It's burning from a clean, predictable source designed specifically for this moment. The result? Consistent thrust, reliable deceleration, repeatable catches. But removing the hot staging ring created a new problem, one that most observers completely missed. On Block 2, that ring sat between ship and booster with deliberate one-sided coverage. During hot staging, when Starship's engines ignited while still attached to the booster, exhaust couldn't escape evenly. The covered section forced flow asymmetrically, physically kicking the booster into its flip maneuver. It was crude but effective, like using a shaped explosive charge instead of a precision instrument. Block 3 eliminates that ring entirely. The hot staging system integrates directly into the booster structure. So how does SpaceX control the flip now? This is where the engineering gets beautiful. Instead of one big mechanical solution, they've orchestrated 3 subtle systems that work in concert. First, engine ignition sequencing. When Starship's vacuum and sea-level Raptors light up during separation, they don't all fire simultaneously. Tiny differences in timing, we're talking milliseconds, create an asymmetric plume environment above the booster. Those pressure differentials impart rotational impulse. Second, that new rounded interstage dome geometry. Exhaust no longer catches on sharp edges. Instead, it flows smoothly across curved surfaces, with heat and force concentrating exactly where SpaceX wants them based on curvature. Look closely at Booster 18's heat map. Those strategically placed reinforcement plates aren't random. They're positioned beneath each engine to channel thermal energy. Third, and this is the detail everyone's debating, intentional asymmetry through the missing grid fin. By removing one fin, SpaceX biases mass distribution, drag profile, and thermal tolerance in a specific direction. That asymmetry combines with plume forces to favor a consistent flip without needing external structures. Some engineers question the offset Raptor vacuum shielding since those engines don't gimbal. But here's what they're missing. While the engines themselves stay fixed, their exhaust absolutely doesn't. At staging altitude, ambient pressure is still high enough that RVAC exhaust is underexpanded. Atmospheric pressure squeezes those plumes inward toward the vehicle centerline. Factor in the gimbaling center engines, and all those exhausts interact like a single flexible flow field rather than separate jets. As the booster rotates away, this combined plume sheet sweeps across the dome. Even a non-gimbaling engine creates asymmetric heating if its plume is being bent by nearby exhaust in vehicle motion. SpaceX can now use strategic gimbaling during separation, steering that combined plume to impinge more strongly on one side of the dome. This creates both thermal loading and a reaction force that initiates rotation. It's more controllable, more tunable, and doesn't require anything disposable. Block 3 hasn't abandoned flip control. It's replaced a blunt mechanical solution with elegant physics. The upper stage transformations are equally dramatic but less visible. Externally, Starship looks familiar, but beneath that steel skin, nearly everything has been rebuilt. Those twin docking ports aren't decorative. They're the enablers of every deep space mission in SpaceX plans. Even though Starship carries immense propellant, most burns away just escaping Earth's gravity well. Orbital refueling makes possible the remaining 400,000-kilometer journey to the Moon or the 225 million-kilometer voyage to Mars. Without it, Starship is trapped in low Earth orbit. With it, the solar system opens up. Other changes tell the story of a maturing design. Repositioned Starlink terminals, refined heat shield taper, eliminated traditional lift points in favor of catch pins and stabilizer points for all ground handling. New orange protective jackets over the COPV tanks. Those composite pressure vessels are incredibly strong, but surprisingly fragile if dropped during assembly. The segmented metal shells with foam padding absorb impacts that could crack the composite layers. Then there's Raptor 3, and this engine deserves its own category of amazement. On December 3rd, SpaceX released footage of a full 6-minute test fire simulating complete ascent burn. Watch closely and you'll see ice forming on the powerhead during operation. This isn't a problem, it's proof of concept. Raptor 3 uses active external cooling, allowing SpaceX to eliminate heavy thermal shielding. Less shielding means less mass. Less mass means more payload. The numbers are staggering. 280 tons of thrust at sea level, 350 seconds specific impulse, just 1,525 kilograms dry weight, and Musk's already targeting 300 tons per engine. A full Block 3 super heavy with 33 Raptors would generate 10,000 tons of thrust at liftoff, enough force to lift a fully loaded aircraft carrier. But none of this matters without infrastructure to launch it. Pad 2 at Starbase represents SpaceX's third-generation launch architecture, incorporating every lesson from Pads 39A, 40, and Pad 1. The tower itself uses stainless steel framework filled with concrete, more integrated and robust than Pad 1's concrete with steel cladding. Chopsticks are shorter, which initially seemed like a limitation until Booster 12 and 14 demonstrated successful catches closer to the tower. That smaller lip on the landing rails works better for recovery. The newly installed, more powerful actuator makes this the most precise catch system yet built. The launch mount eliminated Pad 1's 20 individual Raptor quick disconnects. Best part is no part, cutting complexity, reducing inspections, speeding turnaround. Instead of a donut shape, Pad 2 uses a larger, boxier structure with a water-cooled steel plate mounted on top rather than underneath. This should improve durability as launch cadence increases. The move to dual booster quick disconnects, one for LOX, one for methane, allows faster retraction during launch, reducing exposure to engine exhaust. Underground, the real innovation hides. Most launch sites rely on massive water towers or powerful pumps for their deluge systems. SpaceX chose neither. Instead, they use high-pressure nitrogen gas to push water from storage tanks. Liquid nitrogen boils into gas, expanding enormously and creating pressure without pumps. This makes the system more reliable since there are no moving parts running during launch. At Masses, SpaceX built their most advanced version yet, a system that generates nitrogen gas on demand by circulating water through heat exchangers while liquid nitrogen flows through internal tubes. The water's heat boils the nitrogen instantly, pressurizing the tanks in real time. This allows precise control over water flow rate and pressure, something impossible with gravity-fed towers. Pad 2's deluge can release up to 422,000 gallons per event, static fire, launch, or landing. Most of that, over 300,000 gallons, flashes into steam. About 17,000 gallons get captured by containment systems. The remaining 88,000 gallons flows as shallow runoff or condensation. After each test, leftover water is collected, filtered, and reused. The crown jewel of this infrastructure build-out? SpaceX's new air separation unit. This facility produces liquid oxygen and liquid nitrogen on-site, eliminating hundreds of cryogenic tanker truck deliveries per launch. Using cryogenic distillation to separate oxygen and nitrogen from atmospheric air, the ASU turns Starbase into a self-sufficient propellant production facility. Construction began in July 2025 following Cameron County environmental approvals. By late 2025, the facility has become an increasingly prominent part of Starbase's ground infrastructure. The final piece enabling the rapid launch cadence SpaceX needs to make Mars colonization economically viable. So here's what Block 3 really represents. When most companies upgrade a rocket, they tweak parameters, adjust thrust levels, refine software. SpaceX looked at a vehicle that was already successfully landing and said, let's rebuild it from the ground up. That side-mounted header tank alone required rethinking decades of rocket propellant management. The elimination of the hot staging ring forced engineers to orchestrate flip control through pure physics rather than brute force mechanics. Raptor 3's external cooling system challenges fundamental assumptions about engine design. And Pad 2's nitrogen-driven deluge system plus on-site propellant production? That's not iterating. That's inventing entirely new categories of launch infrastructure. The Booster 18 explosion, tragic as it was, gave us a rare window into this transformation. What we saw wasn't incremental improvement. It was evidence of a company willing to throw away proven designs if better solutions exist. Every Block 3 change serves one goal: making Mars colonization economically viable by driving down cost per launch through radical reliability improvements and faster turnaround times. First flight is coming soon. When that happens, we'll see if SpaceX's gamble on redesigning everything simultaneously pays off. If you want to stay ahead of every development, hit that subscribe button for Space Update 24 hours. Drop a comment below with your prediction. Will Block 3's first flight succeed? And if this breakdown gave you new insights into what makes Block 3 different, share it with someone who needs to understand why this rocket matters. See you in the next one.